Hello guys to another video on my channel. It's been a long time. I have a good reason for not being so active. I was bogged down with my dissertation work. As you know, I'm in a master's program and the final part of the program is a dissertation. So please bear with me. But I have brought you a very interesting looking integral in this video. Let's get started. So consider I to be integral 0 to 1 inverse tangent of square root 2 plus x squared over 1 plus x squared times the square root of 2 plus x squared dx. This is called Ahmed's integral, and this integral, well, is as old as me. There have been several papers and solutions for this, but I'm choosing the one which was first given by the person who devised this problem, Ahmed himself. He called it the maiden solution. It's on archive, and I'll just go through it. It's a very nice, elegant solution for this problem. So first of all, let's use the identity inverse tangent of z or z equals pi over 2 minus tan inverse of 1 over z. The reason for using this kind of identity here is not quite obvious at this point, but we will justify it later on in the video. So then using this identity in the inverse tangent in the numerator, we get I to be pi over 2 integral 0 to 1 dx over 1 plus x squared square root 2 plus x squared minus integral 0 to 1 tan inverse of 1 over square root 2 plus x squared over 1 plus x squared times square root 2 plus x squared dx. Call the first quantity, which is different from this prefactor I1, and the second integral as I2. I1 is quite straightforward actually, so we will do this in the end. We will do the hard bit first. So in I2, we're going to use this identity 1 over a tan inverse of 1 over a is equal to integral 0 to 1 dy over a squared plus y squared. You can look this up in a table of integrals, or you can just do a trigonometric substitution and indeed see that this identity is true. And it is actually this identity that justified us using this first identity, because we already had that factor in the denominator. So in this case, our a is going to be that factor which was in the denominator and in the arctan, the tan inverse. Namely, a was square root 2 plus x squared in I2. It's only because of this factor in the denominator that we can actually justify using the first identity. Without this factor, this entire approach would not have been fruitful. Because trust me, I tried to do this first with Feynman parameter method by differentiating under the integral sign, and that was really not simplifying anything in the end. So with this observation that the factor that was in the tan inverse was also in the denominator, we can write I2 as an integral over two variables because of this yellow identity here. So we have integral 0 to 1 dx dy over 1 plus x squared times 2 plus x squared plus y squared, where the y is the new variable of integration we introduce. Now, when you have a form like this, you want to break this apart into the first factor, a over 1 plus x squared, plus the second factor, b over 2 plus x squared plus y squared. This process is nothing but our favorite partial fraction decomposition. We want this decomposition to equal the original integrand here. So we cross multiply and the denominator vanishes. So all we have left is an equation relating the numerators of the left and right hand side. So If we collect second order terms, which is x squared terms, we have a plus b as the coefficient. And the constant term, because there's no x term, is a times 2 plus y squared plus b. And the right hand side is just the constant 1. There is no x squared dependence on the right hand side, so this a plus b has to be 0, which means a is minus b. And the constant term should be 1 because that's the constant term of the right side. So a times 1 plus y squared, where I've substituted a as b as minus a. So a times 1 plus y squared equals 1, implies that a is 1 over 1 plus y squared. And b is just negative of that. So we know our a and b, we can decompose our integrand into two furthermore integrals. Integral 0 to 1, 0 to 1 dx dy over 1 plus x squared, the first factor from the decomposition, times 1 plus y squared, because that's the coefficient factor, which is coefficient for the partial fraction decomposition, not for this double integral, minus integral 0 to 1, 0 to 1 dx dy over 1 plus y squared, again that coefficient factor, and the second factor 2 plus x squared plus y squared. Now notice this the second integral, you can interchange your x and y variables, so that will not affect the second factor in the denominator, but it will change the y to an x squared. Once that happens, you can see this is exactly I2, the original I2 we started with. See, we just had a y squared, and we do that interchange of variables because it's a definite integral, and the x squared goes to y squared, and the second factor remains the same. So it really is this second integral here. So that's I2. So our entire equation now looks like I2 equals the first integral, which I can write as a product over single integrals. So 0 to 1 dx over 1 plus x squared times 0 to 1 dy over 1 plus y squared, because the factor in the denominator is homogeneous in y and homogeneous in x. You can write that this double integral as a product over single integrals. And again, the second term is just I2. So we have minus I2. We can add this I2 on both sides. So we get 2I2, and we divide by that 2, we get a 1/2 factor. 1/2. This integral is simple. It's inverse tangent of x from 0 to 1, which is pi over 4, and same here. So we have two factors of pi over 4 and a 1/2 from the 2I2. So we have pi squared over 32, because 4 times 4 is 16, times 2 is 32. That's it. That's I2 solved. Let's go back to I1 now. I said this was relatively straightforward because just do a trigonometric substitution. X equals tan theta, dx is secant squared theta d theta. The bounds from 0 to 1 on x now go from 0 to pi over 4 on theta. So we have secant squared theta d theta over secant squared theta from the 1 plus x squared, square root of 2 plus tan squared theta. The secants will cancel. So integral 0 to pi over 4 cosine theta, because the secants cancelled, but I'm writing the tan theta as a sine theta over cosine theta. So that gives me a 2 cosine squared theta, because it was squared, plus sine squared theta, and we have a cosine square theta square root of that in the numerator, which is just a cosine theta. This is just a little algebraic manipulation of a fraction, sine squared theta over cosine squared theta inside a radical in the denominator. Just a little bit of a manipulation. I'm skipping that step. It's quite straightforward. There's nothing tricky or really obscure going on here. So we have cosine theta over 2 cosine squared theta plus sine squared theta. We want to integrate this, the derivative of sine. Cosine is in the numerator, so we would like to have this cosine squared in the denominator to be in terms of sine, so that we can do a nice u substitution. So cosine squared theta is equal to 1 minus sine squared theta from the square relations of trigonometric functions. We have I1 is 0 integral 0 to pi over 4 cosine theta over square root 2 minus sine squared theta, using this relation d theta. Well, we can't we could do a u substitution here. We could say, well, sine theta is u and du is just in the numerator, but then you'd have to do another trigonometric substitution. So instead of that, I'm just skipping those two substitutions, making them into one by saying sine theta equals square root 2 sine of phi, such that cosine theta d theta is square root 2 cosine phi d phi. So fair enough, we have square root 2 cosine phi d phi in the numerator, and then the denominator, using again the square relation over phi instead of theta, we have 2 minus 2 sine squared theta, which is 2 cosine squared theta, under root, so that becomes square root 2, and the square of the cosine drops, so we have cosine phi and square root 2, which cancel identically. Now the slightly tricky bit is the limit. So at 0, at theta equals 0, sine's 0, and phi will be 0. So that's fine, the lower bound's fine. On the upper bound, when theta is pi over 4, sine of pi over 4 is 1 over square root of 2. And you want to find what value phi should satisfy. So we have 1 over square root 2 equals square root 2 sine phi. Bring that square root 2, multiply by the reciprocal. We have sine phi equals 1/2. And what value of phi makes sine go to 1/2? Well, it's pi over 6 or 30 degrees. This is a little fast because, again, this is standard changing variables. You just do that algebra. You plug in for the upper bound and solve for what value of phi you should have. And if you remember your trigonometry, your standard values of sine, cosine, you should know that this will be, the equation will look like sine phi equals 1/2, and then phi has to be pi over 6 or 30 degrees. So, well, the integrand is 1, so we have pi over 6 minus 0, which is pi over 6. So the entire equation looks like I is the prefactor pi over 2 times I1 minus I2, if you remember from before we actually label these things. So we have pi over 2, we know what I1 is, it's pi over 6 times pi over 6, minus I2, we know what I2 is, it's pi squared over 32. So that becomes pi squared over 12 minus pi squared over 32. You can do the LCM, you can do your 5th grade mathematics to get 5 pi squared over 96. That is indeed the final answer. You can verify this. This is indeed the answer. Very neat result with a pi squared. You wouldn't have guessed. You might have guessed there would be a pi because of the tan inverse from experience, but the pi squared is something that is quite neat. It actually comes about because of the double integral, this trick that we did with the double integral, which actually breaks this problem down very nicely, brings partial fraction decomposition into the game when it wasn't, because we had these radicals. Because of this identity that radical squares, then brings partial fraction, and then once we have that, it's to identify the symmetry in this problem. There's an inherent symmetry that we get essentially because of the way this problem is constructed. Because remember, not every definite integral has a nice closed form like this. These challenging definite integrals with nice closed forms are specifically constructed, either be it on integration bees or other kinds of competition, YouTube, Instagram content. So there is usually a nice elegant trick if there is a brute force method. And that's what this channel is for the elegant solutions. Because you learn so much from these tricks. Because now, if I look at a form like this with an arctangent tan inverse of 1 over something over that something, then I will remember this identity from this video that I made on the 16th of August, sorry. And then I will have probably a better chance of uncovering this elegant solution for myself when I'm attempting to solve these problems without assistance from scratch. And that's, anyways, the key takeaway this video. Again, excellent problem, nice solution by Ahmed. So please like, share, and subscribe to my channel, guys. In the meantime, recommend me to your friends, and peace out.